Hey guys, and welcome to our first lesson in probability. So we won't actually be diving in probability just yet. We'll dive in probability in about 2 videos. And the reason is because before we are able to compute probabilities, we have to learn how to count. And I know all of you guys know how to count, but specifically we need to learn how to count the number of outcomes in an experiment. And before we even get to that, we have to understand what an outcome is. So the best way to actually introduce this is to start with a very simple example that I'll put up right now. And the reason I'm doing this is because we have to start from the ground up. I don't want to jump into hard examples right away, because if you guys don't understand the building blocks, then you won't be able to actually use these techniques later when we actually start computing probability. So this section, combinatorial analysis, it's going to take up 2 videos, and they are very important, and you should really keep it in the back of your head after we learn everything. Okay, so let's dig in. So our first example. It goes like this. You roll a 6-sided die. How many different outcomes are possible? So how many different outcomes are possible? Okay. Now, I encourage you guys to pause the video and try every example on your own first before you actually look at how I do it. But we'll be going into the answer shortly. So the question is asking how many different outcomes are possible when I roll one 6-sided die. You can assume this die is fair, meaning that you cannot land a 3 and a 4 at the same time, right? That doesn't really happen in the real world. Once you roll a die, it lands up on one face. You know, if you look down on it, you see one face show up. So what I'm going to do is, I'm going to actually draw all the faces so we could actually see how it looks, right? So we have one face with one dot. Then we have the second face with 2 dots. The third face with 3 dots. Is that how it looks? Oh, I think that's 2 dots. I think it doesn't really matter how it looks, but then we have the 4th face with 4 dots. The 5th face. My squares aren't really squares, but let's pretend they are. The 5th face has 5 dots. And then obviously the 6th face of the cube of the die has 6 dots. So 1, 2, 3, 4, 5, 6. Awesome. So these are all the sides of this 6-sided die, right? We've all seen a die. I just laid out the faces so we can all see them simultaneously. Now, when you roll a die, right, how many outcomes are possible? That's what the question is asking. So let's say I roll it once. Well, I could get a 3 on my first try, right? And let's say I roll it again. I could get a 6. So that's already 2 outcomes. Then I roll it again. And let's say I get a 6 again. Do I count that as a 3rd outcome? Now think about that. The answer is no. And I want you to see why. So let's backtrack. If I roll the die once, I get a 3 first. If I roll it twice, I get the 6 second. And if I roll it the 3rd time, and let's say I get the 6 again, do I count that 6 as a 3rd outcome? The answer is no, because the question is asking how many different outcomes are possible? How many different outcomes? If I roll the 6 again, that isn't different than the 6 I rolled in my second outcome, so we don't count it. So the key word here is different. Okay, so let's say I roll it again, and then I get a 5, and then a 1, and then a 2, and then a 4. So how many different outcomes are possible? 1, 2, 3, 4, 5, 6. Oh, 6 outcomes. That's what an outcome is. So let me get my black die. Let me pen. So in this case, we get 6 outcomes, right? 6 different outcomes. Outcomes. So eventually, what this means is, eventually you will get 6 outcomes. You will get all the 6 sides. If you keep rolling that die, you will get 6 outcomes. Great. Okay, now let's move on to a little harder example. And if you look at this example and you think, okay, we know how to count this, why do we need a whole section on it? Well, it turns out the examples become much harder to really count this way. But we'll do a second example where we will list out all the outcomes, and you'll see why we actually need this section, why we need combinatorial analysis. So here's another example. And it's another die example, but this time you will roll 2 6-sided die. Okay? So you roll 2 6-sided dice. And again, we want to know how many different outcomes are possible. How many different outcomes are possible. Okay. Now, actually, before we move on to this question, I still have something to say about this example. When you roll a die, that's an experiment, okay? In probability, we like to deal with experiments and events and all of that sort of thing. So, when you roll a die the first time, that's one experiment. And when you roll a second time, that's another experiment, and so on. So rolling 1 6-sided die is itself an experiment, okay? And this experiment has 6 outcomes. So that's what it's all about. So in this example, we had one experiment. The experiment was you roll a 6-sided die. That experiment has 6 outcomes. So remember, experiments have outcomes. That's very important. Okay, so now that I said that, try to do this on your own and see how many experiments you can find in this example. So in this example, we have 2 experiments. The 2 experiments are, your first experiment is you roll 1 die, and your second experiment is you roll the other die. So we have 2 6-sided dice. So we have 2 experiments. So experiment 1. Experiment 1 is we roll the first 6-sided die, and I'm going to draw the faces again just so we can see it. So 1, 2, 3, 4, 5, and 6. Okay. So experiment 1 is rolling this 6-sided die, right? And as we saw before, when you roll this 1 die, you get 6 outcomes. So let me write that again. You get 6 outcomes, right? If you roll the first die, in general. Okay, so just ignore this for now. I'll leave it there. And your experiment 2, well, you roll your second six-sided die, right? So experiment 2 is you roll your second six-sided die, and I'll draw it with a red marker. So here's your second die. 1, 2. 1, 2, 3. 1, 2, 3, 4. And then 5. Feel free to skip while I draw, but unless you like to see my horrible drawings. And then we have our sixth die. Okay. Great. And well, by itself, when you roll your other six-sided die, it should also have 6 outcomes, right? Again, the 6 outcomes are, well, you could roll the 1, you could roll the 2, you could roll the 3, the 4, the 5, and the 6. Those are your 6 outcomes. So, again, just ignore this for now, but we'll come back to it. 6 outcomes. Okay? Just for this one die, and 6 outcomes just for this one die. Now, but that's not what the question's asking. The question's asking you roll these 6-sided dice, one after the other, right? That's what it means. And we want to know how many different outcomes are possible. Well, before we get to actually enumerating and listing out all the possibilities, I want to illustrate it for you guys just so you could actually visualize what's happening. So let's say I roll a 1 on my first die, right? I roll it, I get a 1. And then I have to roll my second die. Okay, so then on my second die, I get, let's say, a 1 as well. So what just happened? I rolled a 1 on my first, and then I have to roll my second die. On my second die, I also get a 1. So when I rolled a 1 on my first die, it links to the 1 on the second die because that's what happened. Okay? So let me draw that arrow. This is an arrow pointing to this. Okay? Now, what if I roll a 1 again on my first, but then I get a 2 on my second die? So the 1 on my first die links to the 2 on my second die. Okay? Now, again, let's say I roll a 1 on my first still, but then I get a 3 on my second die. And if you notice the pattern and see what's happening, eventually the 1 will reach all of these outcomes on the second die. If you could just draw the arrows correctly and nicely here. And the last one. Right? Great. So notice something. When I roll a 1 on my first die, I can get a 1 on my second die, right? So, I'll erase this. Okay. So, let's do this. Let's go by the picture and see what's happening. When I roll a 1 on my first die, so I get a 1 on my first die. So, first die, right? The 1 represents your first die outcome because you get a 1. And the first thing we had was a 1 on our second die, right? So we rolled the 1 on our first, and then we rolled the 1 on our second. Okay, so this 1 represents our second die. Second die outcome. Okay? And then what do we have? Well then, Then I rolled a 1 on my first, and then I got a 2 on my second. Oh, so that's a different ordered pair, right? I get a 1 on my first again, but this time I get a 2 on the second die. Okay? And if you notice, this creates the same pattern like we did with the arrows. Okay, you can get a 1 on your first again, but you can get a 3 on your second. Notice how this is creating different outcomes when you roll a 1 on your first, because the second the second number in your ordered pair it's different. You have a 1 here, you have a 2 here, and you have a 3 here. These are all different outcomes for when you roll a 1 on your first die. So we continue this, and I'll just write out the numbers. 4, right? And then you roll a 1 again on your first, but you can get a 5 this time on your second. And then you roll a 1 again on your first, but you can get a 6 on your second die, right? You get a 6 on your second, you can get a 5 on your second, a 4, a 3, a 2, and a 1. But are we done? If we were done, 1, 2, 3, 4, 5, 6. Can we possibly get the same number of outcomes if we just rolled 1 die versus 2 dice? I don't think so. And it's actually pretty easy to see why we're not done, because we only factor in if we roll a 1 on our first die. What about if we rolled a 2 on our first die? Well, if you redraw the arrows for the 2, we create another row of ordered pairs where 2 is now the outcome of your first die, and then you get the 1, right? Then you get the 1 on your second die. So for every 2 you get on your second die, you get another outcome on your, for every 2 you get on your first die, you can get a different outcome on your second die. So if you just repeat the process, you see the pattern. And then you continue for the 3, right? And you continue until, so let me just erase this. You continue until you reach the 6 on your first die, and then you get the corresponding values for your second die. So 6, the 2, you get a 6, and then the 3 on your second die, and then you could get again the 6 on your first, but a 4 on your second, and then you could get a 6 and then a 5 on your second, and then you get a 6 but a 6 on your second. Okay, so how many outcomes do we have? Well, if you actually listed all this out, which I encourage you to do by yourselves, you will end up getting 36 outcomes. 36 outcomes, which is way more than 6 we had in the first example, right? And it should make sense, because for every 1 you get on your first, you could get a 1, a 2, a 3, a 4, a 5, or a 6 on your second. But for every 2 you get on your first, you get a 1, a 2, a 3, or 4, or 5, or 6 on your second. And you keep doing that until you reach your 6 on your first die. And then you count all these outcomes up, and you get 36 outcomes. So in this example, the question was asking how many outcomes, so we got 36 outcomes. Just by listing it out. And if you guys noticed, that took a while, and I didn't even list it out because it would take even longer. So this is why we need combinatorial analysis. This is the whole gist of it. We don't want to list out all the outcomes. We don't, because it's going to take too long, and sometimes it's impossible. Sometimes it just takes longer than a human can live. And this example, it took us probably around 5 minutes. And other examples can take way longer. So combinatorial analysis has certain definitions and theorems that allow us to compute the number of outcomes very quickly and very fast. And this is where the actual section starts. So all this was just to show you guys where it's coming from, why we need combinatorial analysis in general, and now we can begin. So remember, the whole basis is we still want to construct experiments, we still want to understand what they are. Each experiment has its own number of outcomes, okay? Experiment 1 has 6 outcomes, right? Because if you just cover this is just the first example we did. Oh, but experiment 2 also has 6 outcomes because it's also a 6-sided die and has only 6 outcomes. I'm going to leave these 2 here and you'll see why. So I'll erase this. Okay. And we come across our first definition of the course, and it's called the basic principle of counting. So the basic principle of counting and this is what it says. So suppose you have 2 experiments. So suppose you have 2 experiments. If experiment 1, so if experiment 1 results in n outcomes. Remember, experiments have outcomes. So if experiment 1 results in n outcomes, n is our variable, outcomes, and if for each outcome in experiment 1, so if for each outcome in experiment 1, experiment 2 has m outcomes, so experiment 2 has m outcomes, then altogether we have, and this is the big result, we should have n times m. So times m outcomes altogether. So this is how many outcomes we should have. N times m outcomes. And this is a very important definition, and it'll be generalized later for more experiments, but for now, let's think of just 2 experiments, okay? If experiment 1 has a certain number of outcomes, and for each of those outcomes, experiment 2 has another certain number of outcomes, say m, then altogether you should multiply the number of outcomes you had in experiment 1 with the number of outcomes you had in experiment 2. That's what the basic principle of counting says, and the way to prove it is literally just by listing out all of the outcomes that are possible. And we did that specifically for the other example, but you could do it in general. So this is true. So great. And how do we use it? Well, let's think back to this example. So it says first you have to understand what your experiments are, right? So then we label our experiments. We did. We have 2 experiments. And how many outcomes did experiment 1 have? It had 6 outcomes. Okay, so in this case, n, right? N is 6 for experiment 1. Experiment 2 also had 6 outcomes. So in this case, m is 6. And the basic principle of counting says that we have to multiply n by m to find out how many total outcomes are possible given the 2 experiments. So let's do it. Can we multiply n times m? Well, n times m should be 6 times 6. 6 times 6, oh, I know how to do that. That's 36. 36. That's exactly how many outcomes we got before just by listing it out. 36 possible outcomes. And hopefully now you appreciate why we actually need this, because remember before, it took us a while to actually understand how many outcomes there were in general. But the basic principle of counting says all you have to do is multiply the number of outcomes in experiment 1 by the number of outcomes in experiment 2. In this example, we had 6 times 6, 36 possible outcomes. So now you know when you roll 2 6-sided die and they're fair, you should get 36 possible outcomes. Good. Okay. So now we could actually move on to some real examples using the basic principle of counting. So I'll leave it up for now. Erase this. Okay, so here's our example. A community has 100 men. A community has 100 men, each of whom has 5 children. Okay, so each man has 5 children. If one man and one of his children, so if one man and one of his children are to be chosen to win $1,000, how many different outcomes are possible? How many different outcomes, choices, doesn't really matter as long as you understand that outcomes and choices and all of those synonyms are the same. So how many outcomes, how many different outcomes are possible in this example? So again, I encourage you to try this example on your own. A little hint, you have to use the basic principle of counting unless you really want to list out all of the outcomes. Also, it always helps to list out what experiments you're talking about and how many of the experiments there are and how many outcomes you have for each of the experiments, okay? So, a community has 100 men, each man has 5 children. If one man and one of his children are to be chosen to win $1,000, how many outcomes are possible? Well, let's think about this. What are the experiments? So, experiment 1 I say is, well, we have to choose one man. Okay, so we choose a man. Experiment 2. Well, you have to choose one of his children. That's our second experiment, right? We have to choose one of his children. Choose one of his children. Okay. Let's just focus on experiment 1, okay? We have to do this step by step. So, for experiment 1, choosing a man. How many outcomes are there if there are 100 men to choose from? Well, we have 100 men to choose from, so we should have 100 different outcomes, right? We should have 100 different men to choose from. So we have 100 here. So choosing a man gives us 100 different outcomes, right? Because there are 100 men in the first place. So I could pick Bob, I could pick John, but in general, you know, you go by the names and you'll see you have 100 different men to choose from. You can't get more and you can't get less. Okay, now let's focus on experiment 2. We have to choose one of his children, one of the man's children. Well, how many children do we have to pick from? Choose one of his children, one of the man's children. So you pick one man, let's say Bob, and Bob has 5 children. How many choices, how many outcomes do we have from Bob's 5 children? Well, we only have 5, right? We have only 5 of Bob's children to choose from. So 5 in this case. Now, if you said 500, good guess, but that's wrong because the second experiment is you're choosing one of the man's children and each man has 5 children. How do we know that this is experiment 2? Well, the question says if one man and one of his children are to be chosen to win the $1,000, right? It's not saying that any child from any man. It's saying what if you pick a man here, then one of his children are going to be picked here, and each man has 5 children. Okay. So we have 2 experiments. We have the outcomes for each experiment. Oh, the basic principle of counting says if you have 2 experiments and you know the number of outcomes for each, just multiply them and then you find out how many total outcomes you have. Okay, 100 times 5. 100 times 5 is 500. 500 different outcomes. And that's all there is to it. If you didn't understand that you had to multiply this, and if you never learned the basic principle of counting, well, imagine listing out 100 men, and then for each of those men, you have to list out 5 children. So I don't know how you would list that out. You would probably have to make up names for each of the 100 men. But intuitively, it should actually make sense that you should just multiply these 2 numbers to get 500, because remember, each man has 5 children. Each, you sort of think of multiplication in general. So, but the basic principle of counting gives you that intuition anyway. You just multiply and by hand. And that's it. Okay. Let's move on to our next example. I'm going to erase the basic principle of counting, so make sure you have it in your notes. Okay. So this first section can get a little tricky later on, and you'll see how. But I promise you it will get a lot easier once you get more examples in, and once we actually get to computing probabilities, it shouldn't be too bad. So if you feel like you're gonna get stuck in the later examples, don't discourage yourself. They will get easier, and if you don't understand my solution, or if you don't understand how I reason through the question, please leave down the comment below, and I'll try to get back to you as soon as possible with ways to help you. Okay, so this is a segue to the generalized basic principle of counting. So now we want to generalize it, and I'll just reference it as this, the generalized. So this is our second definition. Generalized basic dot principle dot counting. So I'm just gonna write it like this. So this is the basic principle of counting, but it's generalized. And I'm gonna basically just write a shorter version of this, but you guys will understand what's gonna be going on. So instead of having 2 experiments, we have k experiments, okay? So you have k experiments. Okay, so you have k experiments. So let's say, first experiment has n1 outcomes, your second experiment has n2 outcomes, and then your kth experiment has nk outcomes. Okay, so if experiment 1 has n1 outcomes, and for each of these outcomes, so if experiment 1 has n1 outcomes, and for each of those, so those n1 outcomes, experiment 2 has n2 outcomes, and then you move on, blah blah blah, and then experiment k has nk outcomes, then altogether you have n1 times n2 times n3 times blah 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 times nk. Okay, so this is how many possible outcomes you have for k experiments. Now, don't get lost in the notation, and don't be confused by this definition, because I guarantee you could just draw this back to the basic principle of counting. So let's say we again had 2 experiments, right? Oh, so then you would just have n1 times n2, just like we have with the basic principle of counting. Instead, we just had n times m. I'm just using different notation because this time we have k experiments. Oh, when you have k experiments, you multiply all the outcomes in all of those experiments, right? So if we had, let's say, 5 experiments, or three experiments, oh, then you would just have this, n1 times n2 times n3. Okay, so the index here, the 1 to the 3, is just to let you know what experiment you're talking about. Because when you have 2 experiments, you just need the 2 letters. But when you have k experiments, we like to use this index just to refer back to what experiment we're talking about. And then the n is the actual number of outcomes for those experiments. So let's say like n1 in the first example when we had 6 times 6. Well, 1 refers to the first experiment, and then the n refers to our 6 outcomes. The 2 refers to our second experiment, and the n refers to our 6 outcomes. So that's how you should look at it. Please don't get lost in this definition, but it is very helpful, as you'll see in the next example. And you'll see that actually using this isn't as bad as it seems. So let's get straight to it. So let's see. So this is a two-part example. So example part A. So how many different, let me draw a line here just to separate this. How many different 5-place license plates are possible if the first two places are occupied did I spell that right? Typical math student spelling English words wrong. Occupied, I don't know if I spelled that right, but it doesn't matter. By letters. So, so the question is asking how many different 5-place license plates are possible if the first two places are occupied by letters and the last three places are occupied by digits. Occupied by digits, numbers. I like digits because we actually know what we're talking about, 0 to 9. So, okay. How many different 5-place license plates are possible if the first two places are occupied by letters and the last three places are occupied by digits? So for this example, we're going to actually refer to this example a lot. So we're going to have a special technique of doing this, and it still follows the experiment thing, but in a little different way. So we have a 5-place license plate, right? So how do we deal with that? Well, think of the license plate 1, 2, 3, 4, 5 with, I'm gonna do that too high. Do a license plate 1, 2, 3, 4, 5, right? It has 5 places. 1, 2, 3, 4, 5. And the question says that the first two places are occupied by letters. And you could assume the English alphabet for this, right? So 26 letters. Okay, so the first two places are occupied by letters. So I drew a divider here to illustrate that these two are letters. And then the last three places, 1, 2, 3, are occupied by digits. Okay, so 1, 2, 3 are occupied by digits. And we want to know how many different, alright, so we want to know how many different outcomes are possible. How many different 5-place license plates can we create? Okay, so we have to somehow use the generalized basic principle of counting, right? So how many experiments do we have here? Well, I say 5, and this is the reason I say that. Choosing one letter here is your first experiment. Choosing something else here is your second experiment. Choosing something else here is your third. That's your fourth experiment, and that's your fifth. Okay? So, experiment 1. Well, experiment 1, you have to choose a letter. You have to choose a letter from the English alphabet. The English alphabet has 26 letters. So how many possible outcomes can we get in our first experiment? Remember, our first experiment is choosing a letter from the English alphabet. Well, if I could choose any letter I want out of the 26, well, then we should have 26 outcomes, right? So we have 26 outcomes for experiment 1. The second place of the license plate is also occupied by a letter. Well, we still could choose any letter we want, right? The question doesn't say we cannot repeat a letter. So we still have 26 letters to choose from. So let's say I chose A here, right? I can still choose A again. The question doesn't say I can't choose A, so we still have 26 letters to choose from. So that's for experiment 2. So experiment 1 has 26 outcomes. Experiment 2 has 26 outcomes as well. Great. Now we move on to the 3 places here, and these 3 places are occupied by digits. The digits are from 0 to 9, so 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We have 10 digits to choose from, right? So for experiment 3, we have 10 digits to choose from, 0 through 9. There's 10 digits, so we can choose any digit we want out of the 10. So we have 10. So again, we could repeat a digit, right? The question doesn't say I can't choose, let's say I chose 1 here. I could choose 1 again here. So we have 10 digits to choose from again for experiment 4. And then for experiment 5, you're still choosing a digit, and we still could choose any of the 10 digits that there are. So there's 10. So, okay, so what do we do? Experiment 1, you choose a letter from the English alphabet, right? Because the first 2 places are occupied by letters. So for experiment 1, you have 26 outcomes. You have 26 outcomes because we could choose any letter from the English alphabet that has 26 letters. So experiment 1 has 26 outcomes. Experiment 2 also has 26 outcomes because we could choose, again, any letter we want from the 26. Experiment 3 has 10. Experiment 4 has 10, and experiment 5 has 10 outcomes. Awesome. So we have 5 experiments. 5 experiments. And the generalized basic principle of counting says if you have a certain number of experiments and each of those experiments has a certain number of outcomes, all you have to do is multiply it all together to get the total possible outcomes. Okay, so we got all the outcomes here, and now we just have to multiply them, and that's it. That's all we have to do. So once you multiply this, you get 676,000 outcomes. Awesome. 676,000 different license plates, right? Different 5-place license plate. You have 5 places here. Think of when you're driving, you see someone's car, you see that they have 5 places, and the first 2 places are occupied by letters. So for example, you could have someone's license plate be like A, B, 4, 0, and 1, right? So this is just one type of outcome out of the 676,000 outcomes out there. And that's actually crazy to think about. So, yeah, and remember, you could repeat anything you want. So you could have had AA 444, which is again another outcome out of all of these types of outcomes for your license plate. Yeah, that's it. So I did say this is a 2-part example, so here comes the second part, and I'll put it up here, so I'll erase this. So here we go. So remember, the generalized version basic principle of counting says, as long as we have a certain number of experiments, and each of those experiments have a certain number of outcomes, all you have to do is just multiply them together. Okay, so part B says, what if repetition of letters and numbers isn't allowed? Okay. So this would be okay, right? Because we're not repeating any letter and we're not repeating any number. This would not be okay for this example. It would not be okay because we repeated an A, and that's already bad. And also we repeated the 4s, which is, even worse. So this question says, what if repetition is allowed? And intuitively, do you think we should have less outcomes or more? So think about that. So, okay. So I would still draw this out, right? Because we still have 5 different experiments. We have 5 different experiments. And for experiment 1, so we just started, right? It's our first experiment, and we have to choose a letter from the 26. Well, we still haven't chosen the letter yet, and we have 26 letters to choose from. So we still have 26 outcomes, right, for experiment 1. And let's say I chose A. So in this example, part B says I cannot take A here, okay? It's illegal. I cannot have an A. So if I can't have an A, that means, well, I only have 25 letters from the English alphabet to choose from, right? Because you minus the A out, you only have 25 letters left. Oh, so experiment 2 has 25 choices or outcomes that you can pick, right? You can pick anything from B to Z. You just cannot pick A. Because the question says you can. Here you could, here you can't. Okay, so experiment 1 has 26. Experiment 2 has 25 outcomes. Now we move on to our 3 places that are occupied by digits. So we haven't picked any digits yet. So our third experiment, you could pick any of the 10 digits you want, just like we had before. And let's say I pick the 1. Oh, but I can't pick the 1 here anymore, right? Because repetition isn't allowed. So I could pick anything from 0, 2, and then up to 9. So 2 through 9, you have 8, and then plus the 0, you have 9. 9 different digits. Okay. So you have 9 different digits for experiment 4 to choose from, right? Because you can't pick the 1 anymore. And let's say I chose 0 this time. Oh, but I can't choose a 1 or a 0 here. I can't choose both of them, actually. So if I can't choose 1 or 0, well, that only leaves me with 8 different digits, right? The digits 2 through 9, that's 8. So, okay, I only have 8 different digits to choose from. And that's it. So if you see here already, this is going to lower our number of outcomes. And it should make sense, right? Because if repetition isn't allowed, that means you cannot have more outcomes than if repetition is allowed. So this turns out to be 468,000 different license plates or outcomes. And that's it. So remember, you can't choose A again, Here you can't choose A again, for example. We could have chosen B here, and you can't choose the B here, but it still mathematically means that you can't choose that one letter, so you only have 25 letters to choose from anyway. So it doesn't really matter what you choose, but if this helps you sort of see what's going on, please do it. So that answers that question. And okay. So this is our last example before we move on to permutations, and this example is actually a little tricky. Well, not that tricky, but it's a little abstract. So stand by. You just have to sort of understand what the question's asking at first, and then it doesn't become too hard. But remember, you always have to bring it back to what we've just learned. You always have to bring back the question, can I use the basic principle of counting here? Can I use the generalized version of it somehow? So I'll write up the example, and I encourage you to try it on your own. So here it goes. Okay, so we want to know how many functions, defined on n points are possible how many functions defined on n points are possible if each functional value is either 0 or 1. Okay. So I told you guys we'd be counting, right? We'd be counting the number of functions. So you can already see why we actually just needed what we needed, right? I mean, how would you even draw this out? You can. It takes even longer than the second example we did. So we have to somehow use the basic principle of counting somehow, somewhere. But first, we have to understand what are we even trying to find? You know, what are we doing here? Well, we have to count the number of functions that are defined on n points whose functional value gives you a 0 or a 1. So what does this even mean? What does it mean for a function to be defined on n points? Well, a function is defined on what? Think back to calculus. Think back to, anything you know about functions. Functions, they are defined on a certain domain, right? Because your domain has, let's say, x values, and you input those x values from your domain into your function, and you get out an output. And your output is your functional value. So that's what it is. So this is your input. That's your output. Your inputs are in the set of the domain. Your outputs are in the set of your range. Okay, so you have a function whose domain maps to its range, right? Okay, so this, don't worry about this. That's just for me. So your domain has n points. So 1, 2, 3, n. Something bracket. And your range, so basically, the question is saying you have a function defined on n points, so it's defined by this domain, and every input can give you either a 0 or a 1. And we want to know how many functions have this domain that map to this range, right? So how many functions are possible? Well, let's do a simpler example first, okay? I think the domain is a bit too big. So let's focus on a smaller domain. So let's say, just for our sake, that domain instead only had 3 points, okay, instead of n. Okay, so you have the numbers 1, 2, and 3 in your domain. And your range, well, we'll keep it 0, 1, right, because that's simple enough. So, just to backtrack a little, again, a functional value of 0 or 1 just means that your range is 0 and 1. And a function defined on n points is defined on a domain with n points. Okay, so a function is mapped from its domain to its range, right? So let's work on our first experiment. So experiment 1. So let's say it's defined as f of x, right? So these are your x values. So experiment 1 is choosing x equals 1. Experiment 2 is choosing x equals 2, right? And experiment is down. Experiment 3 is you choose x equals 3. Okay, so notice something first. We have 3 experiments because we have 3 different inputs in our domain. So that's what you should notice first, so we can work with this in this example. So experiment. Okay, so because we have 3 inputs, we have 3 different experiments. So let's focus on our first experiment. So what's the goal? We have to find the number of outcomes for each experiment. So experiment 1, let's focus on this first. Well, f of 1, your function, can get either a 0, it can get either a 0, or it could get either a 1, right? It cannot get both because that's not a function. So your function, when you input 1, can get either a 0 or it could get a 1, right? The or is important. Just like when you roll a die, you can't get a 1 and a 3. You could get 1 or a 3, right? So here you could get a 0 or a 1. Oh, this is 2 outcomes, right? Because you could get either a 0 or 1. That's just 2 outcomes. So you have 2 outcomes for experiment 1. Now, what if our input is 2? Well, again, you could get either a 0 or a 1, right? Because our range is only 0, 1. So when you input 2, you could get a 0, or you could get a 1. Again, 2 outcomes, right, for experiment 2. Okay, so I'll write 2 outcomes here. So 2 outcomes. Now what about experiment 3 when you choose x equals 3? Well, it's the same thing because you only have 0 and 1 in your range. So you can get either a 0 or f of 3 equals 1. So again, you only have 2 outcomes. Great. So we found all the experiments. Your experiments are your domain values, right? Because you only have 3 inputs to choose from. X equals 1, x equals 2, x equals 3. We have to find the outcomes for each experiment. 2 outcomes for experiment 1, because f of 1 can equal 0, right? F of 1 can equal 0. Think of the dice example. Or f of 1 can equal 1. 2 outcomes. Experiment 2 is when x equals 2 and f of 2 can equal 0 or 1, right? It can equal 0 or it can equal 1. So you get 2 outcomes again. 2. And same thing for experiment 3, right? You can also get 2 outcomes because the 3 maps to the 0 or the 3 maps to the 1. So the generalized basic principle of counting says if you have 3 experiments and you have a certain number of outcomes for each experiment, all you have to do is multiply the number of outcomes together. So 2 times 2 times 2, which is 2/3, right? 2 to the 3. Oh, but that's just 8. 8 outcomes. 8 different functions. 8 different functions that have this domain that map to this range. That's what you just found. You found 8, well, you counted 8 different functions that have this domain that map to this range. That have this domain, this arrow means you map to this range. Great. 2 times 2 times 2, 2 to the 3rd equals 8. Notice something. If you just cover this, it's the same example, right? You get 2 to the 3rd number of outcomes. Now we don't have 3 experiments, right? Because our experiments were our x values. Instead of 3 experiments, you have n experiments. You have n experiments, each of whom has 2 outcomes. So you have n experiments, each with 2 outcomes. So what does this mean? Well, notice how here we had 2 to the third. 3 is the number of experiments. Here we have n experiments, so you should have 2 to the n. You should have 2 to the n possible functions. And that's it. That's really the whole example. So how do I get from here to here? Well, when you have 3 experiments, you have 2 outcomes for each experiment, you multiply them together, you have this nice little pattern, 2 to the third equals 8. If you had 4 experiments, you would have 2 to the fourth. If you had 5, you would have 2 to the fifth. If you have n, you have 2 to the n. And possible functions that have this domain that map to this range. Okay? So 2 to the n functions like this. Functions like this. That's all it means. So remember, when a function is defined on endpoints, that just means it's defined on this domain that has endpoints. And when a functional value is either 0 or 1, that means its range has the values 0 and 1. And each of these values, right, 1 can map to 0 or map to 1. 2 can map to 0 or can map to 1. 3 can map to 0 or 3 can map to 1. Remember, that's how basically what we did here in the smaller version. This is just on a bigger scale, but as long as you can do this and bring it up here, that's all there is to it. Okay, so moving on to our next example. Oh, sorry, not example. Our next topic, it's on permutations. So let me erase this. If this example didn't come clear to you, please leave down a comment and I'll try to explain it even more thoroughly than I did here. I really want you guys to make sure you understand this before we move on. So the harder part of this example is just understanding what these terms mean. And I think once you understand that, it's not so bad. Again, just remember a function is just defined to its range. That's all I'll say. And each experiment relates to the number of inputs in the domain. And that's it. But again, if you don't understand that, please leave down the comment. Don't just avoid it and say, oh, it's okay, I need to know this. I mean, it's not something, this example isn't going to show up a billion other times, but it's a good example to really make sure you understand that, what the goal is. You have to find the experiment, you have to find the number of outcomes for that experiment, and then you just have to multiply the number of outcomes, and then you get the total number of outcomes for the total experiment. Okay. So, permutations. And you're probably already familiar with permutations from high school or middle school or even college or university. And you're probably gonna, be familiar with whatever I'll be writing down shortly, but there's still a little more to it than you've probably seen in middle school. But we'll get straight to it. Permutations are very important, but what we learn after permutations in the next video, combinations are even more important. But what we will learn right now is very key to understanding combinations later on, so it's very important to understand what permutations are in general. So the best way to actually introduce permutations is by starting an example. So let's just do it. It's not really an example, it's just something to get to the definition of a permutation. So how many many different ordered arrangements of the letters X, Y, and Z are possible. Okay. So we already know how to do this using the basic principle of counting, right? All you would do is, well, let's think about the license plates example. We have 3 different letters. 1, 2, 3. And we want to know how many different ordered arrangements of the letters are possible, right? So we have only 3 letters to choose from. So instead of the 26 from the English alphabet, for example, this time we just have the X, Y, and Z. How many different outcomes can I get in my first experiment? Well, I have 3 different letters to choose from. I haven't chosen one yet, so I could choose 3 to be in my first place. Any of the 3, right? I could choose X or Y or Z. But since we only have 3 letters and I chose 1, we only have 2 left, right? So then I have 2 for my second experiment. And then I chose X and Y, for example. Oh, but then I have 1 letter left. So 6. 6 different ordered arrangements. Now, let me list it out. Let's list this out. So listing it out, just to illustrate something. So we should get 6 different arrangements, right? So let's do that. Well, the first arrangement is the easiest one, I think, X, Y, Z, right? Okay. Well, what if I could get X, Z, Y, right? These are different. Y, X, Z, Y, Z, X, right? So for the 2 X's, you can switch to Y and Z. For the 2 Y's in the first place, you can switch to X and Z. And then when Z is in first place, you get X and then Y, or you could get Z and then Y and then X. And I cannot think of any more arrangements. If you can, then you're more genius than I am. But this tells us we should have 6. So 1, 2, 3, 4, 5, and 6. Exactly what we got. And, you know, how does this relate to permutations? You know, what's going on? Well, each of these arrangements is a permutation. Permutation. That's what a permutation is. Let's spell that completely wrong. Permutation. A permutation is an ordered arrangement. Okay? Each of these are permutations. So in this case, you have 6 permutations. Permutations. Okay, so it's an ordered arrangement, and that should tell you, that should tell you that in a permutation, order really matters. It insanely matters. Why does it matter? Well, if a permutation is an ordered arrangement, that tells you that, for example, these 2 arrangements are different, even though they have the same objects. By objects, so in this case, X is an object, right? It's a letter, it's an object. Y is an object, and Z is an object. Even though these 2 arrangements have the same letters, they have different order to them, right? Even though they have the same objects, they are in different order, so they are different permutations. They are permutations. They are different ordered arrangements. So that's why order matters. So order matters Order matters in permutations because it distinguishes different arrangements. Different arrangements with the same objects. Okay? With the same objects. Again, what are the objects? X, Y, and Z, right? They're objects, they're letters. So order matters because it distinguishes these two arrangements even though they have the same objects, which are Z, X, and Y. But because the order is different, we have six permutations. So that's what a permutation is. Again, how do we get 6 here? Well, we use the basic principle of counting, right? Experiment 1 has 3 outcomes. You have 3 different letters to choose from. Once you have chosen one object, you can't choose it again, right? Because they're objects. They're not like infinite letters that you can choose from. Then you only have 2 letters to choose from in your second experiment. And then you have only 1 left in your third experiment. The basic principle of counting says you have to multiply every experiment and the number of outcomes for those experiments together, and you get 6. And that's it. And you're probably wondering, how is this different than what we've just done? Well, it is different because permutations have a certain pattern. And if you see it right now, good. If you don't, I'll write it right now. So let's see. I'll erase this. Keep the above. So here we had 3 objects, right? X, Y, and Z. Now I want to generalize it for more than 3 objects. What if I say n objects, right? N objects. So generalizing to n objects. We have n times n minus 1 times n minus 2 times n minus 3 times blah 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 times 3 times 2 times 1 different permutations. Okay? This is defined to be n factorial. And I'll explain what that is right now, if you haven't seen it before. N factorial, the factorial symbol looks like an exclamation point. So, what does it mean? It means that when you start off with n factorial, you work your way down minus 1 from n and you multiply all those numbers together. So, this is 3 factorial because you start with 3 and then you multiply by a number that's 1 less from 3. Oh, and then you multiply it by another number that's 1 less from 2 and 2 less from 3, right? So 3 times 2 times 1 is 3 factorial. N times a number less than n by 1 times a number that is less than n by 2, blah blah blah, until you reach 3 times 2 times 1 is defined as n factorial, right? So whenever you see n factorial, it is this. Whenever you see this, it is that. That's how it's defined. So for example, 5 factorial, just as an example, 5 factorial is 5 times 5 minus 1, 4 times 5 minus 2, 3 times 5 minus 3, 2 times 5 minus 4, so you have n minus 4 here, times 1. Oh, and that's it. I think that's 120. Doesn't really matter what the answer is, as long as you understand what the factorial means. And you're probably thinking, okay, what's going on? Why do we even need this if I could just multiply this and not worry about this weird symbol? Well, it turns out that this symbol will actually make the math much easier condense everything later on in combinations, and it'll give you the bigger picture much clearer. And it's not as intimidating as it is. As long as you remember what it means, you're just multiplying a bunch of terms together where each term decreases by 1 from your first term. That's defined by n here. And if you have a scientific calculator, it could literally just do this for you and you don't have to think about it. So, don't think about it too hard, but make sure you understand what it means, right? So you start with your n, 3, and then you multiply by a term that's 1 less than 3 in the second place, and then you multiply by a number that's less than 3 by 2 in your third place, right? So, like that. And also, 1 factorial is 1, and 0 factorial is also 1. Okay, so that's how it's defined. So don't forget that. So 0 factorial is 1. That's how it is defined. It's just a special case that doesn't fit into this definition. So don't worry about it too much, but just know if you ever see 0 factorial or 1 factorial, it's just 1. And that's it. 2 factorial should be this, right? So 2 times 2 minus 1, 2 times 1 is 2. And that's it. Okay. So let's actually move on to an example that really uses the factorial sort of pattern and a permutation. So I'll erase this. So everything we did before permutations was basically just counting, counting the number of outcomes. Permutation is also that, but it's a special case. So, okay, here's our example. A class consists of 4 men and 6 women. Consists of 4 men and 6 women. The students are ranked by their GPA. It's kind of cruel, but the students are ranked by their GPA. GPA is grade point average, which is just your grade for the semester or year. Assuming no 2 students have the same grade, so assuming no 2 students have the same grade. So this is a 2-part example. So here's part A. How many different rankings are possible? How many different rankings are possible? So never forget what the goal is. Always try to find your experiments. Always try to find the outcomes for those experiments, and use the basic principle of counting or the general version of that. Of course the general version is the more important one, but if you have 2 experiments, it doesn't really matter. You can still use the general version of it. Okay, so we want to know how many different rankings are possible if the students are ranked by their GPA, and assuming that no 2 students can get the same grade, right? Well, what do we know? Well, how many students do we have in general? We have 10 students, right? 4 men and 6 women. 6 plus 4 is 10. So we know we have 10 students. So 10 students. And they're ranked. They're ranked So when I think of ranking, I think of places, right? So first place, second place, third place. So let's draw them out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And all of these 10 students are ranked by their GPA, and no two students can get the same grade. Okay. So over here we have an experiment, right? This is our experiment 1. We're choosing a student from the 10 students who have a certain GPA, right? So we want someone here in first place for experiment 1, and how many students can we choose from the 10 students that has the highest GPA? Well, we have 10 students to choose from, right? It could be any of them. So experiment 1 has 10 outcomes. Let's say we choose Bob, and he's in first place. He had the highest GPA, so Bob is out of the 10 students, right? So we have 10 students to choose from. We chose Bob. So 10 students to choose from in experiment 1, 10 outcomes. Once we have chosen Bob, we don't have 10 students anymore, right? We have 9 other students left. 9 other students to get the second place. Oh, so 9 students for experiment 2. I don't know. Ashley has the second highest grade, and she's mad at Bob. Okay. Once we have chosen Bob and Ashley for the second and first place, well, for the third place, we don't have 9 students anymore. We only have 8 students to choose from, right? This is the same type of example, like the license plates example, like all those other examples. It's basically the same thing, except now you'll see that we have a certain pattern. Okay, and once we have chosen one of the 8, we only have 7 students left, and then we continue down. Awesome. Oh, so 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. What did we just talk about? That definition, the factorial, the exclamation point thing, like what is that? Oh, wait, 9 is less than 10 by 1, 8 is less than 9 by 1, 7 is less than 8 by 1, and I'm multiplying all these numbers together, and I reach 3 times 2 times 1. I recognize this as 10 factorial, right? That's how I recognize it, at least. It is 10 factorial. Yeah, you could just multiply this all up, and you get, so 10 factorial, and this is 3,628,000 different rankings, which is actually a lot. Wow. So 3,628,000 possible rankings. Okay. So 10 factorial. So remember, a factorial, if you look back in your notes, is defined like this. You start with your n, and you work your way down, and you multiply all those numbers together until you reach 1. That is the 10 factorial right there. But you still use the, ignoring this for a second, you still use the basic principle of counting, right? Because you're multiplying all the outcomes in your experiments. You still understood what the experiments were, right? Experiment 1 is choosing a student for your first place. Experiment 2 is choosing a student for your second place, and so on. Okay, so let's move on to part B. So what if the men are ranked among themselves and the women are ranked among themselves. Okay. So when I read this question, I think of like a separation, right? Kind of like the license plates example when we had the letters in the first two places and then the digits in the three places. This time we should have 4 men in the first few places and 6 women in the last few places, right? Or it could be the other way around, 6 women in the first 6 places and 4 in the last, but it turns out it doesn't matter because all you're doing is just multiplying and then you will get the same exact answer. So we still have 10 places, right? So we still have 10 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Except this time the men are ranked among themselves. So you should have 4 places for the men, right? Because we have 4 men. And you should have 6 spaces for the women. So this looks exactly like the license plates example, except we'll have this nice pattern of the factorial, as you will see again. Okay, so let's start with experiment 1 in the men's section. How many men can I choose to be in the first place? Well, I have 4 men to choose from, and only one of them can be in first place because no 2 men can get the same grade, right? So you can't get a tie. So I only could choose 1 man here from the 4. So I have 4 different men to choose from, right? Oh, but once I've chosen Bob for first place, I can't choose him again. So I only have 3 other men to choose from for our second experiment. So that's 3 outcomes for second experiment. And once I've chosen Bob and Dylan, I only have 2 other men to choose from. And then once you've chosen that guy, you only have 1 other guy to choose from. And that deals with the men, right? Because the men are ranked among themselves. You know, Bob is in first place, Dylan is in second place, Mike is in third, and Paul, which is me, is in 4th place. Okay, now we have to deal with the woman. Well, it's exactly the same thing, right? Because for the first place, you have 6 different women to choose from. So this is like experiment 5, you have 6 different outcomes for experiment 5, where you're choosing a woman. And then once you've chosen Ashley, you only have 5 other women to choose from. And if you notice the pattern, it's exactly the same thing. 6 times 4 times 3 times 2 times 1. 6 times 5, sorry. Times 4 times 3 times 2 times 1. And you can multiply all this together, right? You have to multiply all these numbers together because the basic principle of counting says if you have a certain number of experiments, in this case you have 10 experiments, each has their own certain number of outcomes, right? Experiment 1 has 4 outcomes. Experiment 2 has 3 outcomes. Experiment 3 has 2 outcomes, and so on. So the basic principle of counting says you have to multiply all of this together. You get a number. But before I do that, I just want to illustrate that this is 4 factorial times 6 factorial, right? Because right? This is 4 factorial. Horrible bracket or whatever. This is 4 factorial. And this is 6 factorial. If you notice, because the 4 is here, right? And you go 3 times 2 times 1. That's 6 factorial. You multiply them together. That's how many outcomes you get. And this turns out to be 17,280 different rankings, which is a crazy big difference from this. So notice, just if the men are ranked among themselves and the women are ranked among themselves, you get a lot less outcomes, which is nice to think about why that is. Okay. So that's a good example to see how factorial works. And our next example is a bit tricky because when you think you're done, you're not actually done, and you'll see why. But I hope I've explained this example good enough for you guys. I hope you understand the factorial, where it's coming from. Just look back at the definition of what the factorial is, the n exclamation point and factorial. And always try to bring it down to this, because again, in the next section, it will be very helpful to be able to understand what this means. And yeah, that's all there is to that. Okay, so let's start our tricky example. I mean, it is tricky, but it's doable. You have all the tools that you just learned to solve this example. It's just a little tricky, but I believe in you guys. But remember, I encourage you to do it yourself, and if you can't, that's fine, because I mean, math is about making mistakes. Like, everyone makes mistakes in mathematics. No one is perfect, and don't get discouraged when you make a mistake. It's it's a learning process. Math is fun, it's exciting, and understanding how to solve the problem, once you actually solve it, it's the best feeling in the world. So don't give up. Again, if you can't solve the problem on the first try, it's fine. Just look at my solution, and this way you understand where you went wrong. It could have been just a stupid algebra mistake. I do it all the time. Or it just could have been that you don't understand the concept, which is fine. Just understand that if you don't understand the concept, rewind, look at your notes, look at my solution, and see where you went wrong. And if you still don't understand it, again, I encourage you to leave a comment in the comment section below. Okay, so let's start this example. Okay, so I'll just, highlight that it's tricky. I don't know, maybe it's not that tricky, but we'll see how you guys do. So, okay, it's a big word problem. And if you notice, we have a lot of word problems, and you should get used to that in probability. It's not going to be heavy proof class, maybe a couple proofs, not that many, probably 2 to 3 proofs to be honest. And the reason is because I want you guys to see the application of probability instead of just the dryness of the proofs. So that's why you see a lot of word problems. Okay. All right. So here it is. So suppose you have x. Oh boy. Suppose you have 10 books, and you want to align them on your bookshelf. That you want to put on your bookshelf. Okay, so you have 10 books. Of these 10 books, of these 10 books, 4 of them are math books, of course, right? Because you're a mathematician. 4 math books. So I'll just abbreviate 4 math. 3 English books. You have 2 chemistry. And you have 1 history book. So you have 1 history book. Okay, so out of these 10, you have 4 math, 3 English, 2 chemistry, and 1 history. If you count them all up, that is 10, 4 plus 3 plus 2 plus 1. So, if you were, oh my god, if you were to align, the books so that the books dealing with the same subject, books dealing with the same subject are together on the shelf, on the shelf, how many arrangements are possible? How many different permutations or arrangements, how many different arrangements are possible? Okay, big example. Okay, so again, try this on your own, but we'll get straight to it. So, what does the problem set even say? You want to align these books so that the books that deal with the same subject are together. So I guess the 4 math books are together, right? The English books are together, and so on. So let me draw that over here. Let's draw our bookshelf, or try to draw it. So you have 1 math book, 1 English, your 2nd math book, your 3rd math book, and your 4th math book. Then you have your English books. I don't like how I show that. Then your 2 chemistry books, right? Chemistry 1, chemistry 2. And then your 1 lonely history book. Okay? So you have 4 math books, 3 English books, 2 chemistry books, and 1 history book on your bookshelf. This is just one type of arrangement that's allowed. You cannot have, so this is good. This is just one of the possible arrangements. What you can't have is, for example, math 1, math 2. That just illustrates that this is like your 2nd math book, this is your 1st. You cannot have like an English book between your math books, for example. This is already bad. This is not allowed. This is like illegal for you. You don't want English to intrude in your math books, okay? So this is bad. So this is a plausible arrangement. This is not. So, knowing that, we want to find the total number of arrangements that are possible. How many different ways can I rearrange my books on this bookshelf? Knowing that the math books have to stay with themselves, the English books have to stay with themselves, and so on. Well, let's just start off with how many different ways can I rearrange the books regarding their own subject. Okay, so let's do that first. So what do I mean by that? Well, let's deal with the math books. Big M for math. And we have 4 different math books, right? There are 4 different math books. There are 4 different objects. Remember the objects. They are objects, correct? So, let's say they're on the shelf just by themselves. How many different ways can I rearrange these math books? Oh, this just boils down to the same problem we've been doing. So, in my first place, I could choose any of the 4 math books I want, right? Any of the 4. So experiment 1 is you're choosing a math book, right? So you're choosing any of the 4 math books. So experiment 1, for example, has 4 outcomes. Once I've chosen 1 math book to be in the first place, let's say I chose this, I only have 3 math books left to choose from for my second experiment. Once I've chosen the 2 math books, I only have 2 left for my third place. And then once I've chosen all 3, I have 1 math book left in the last place. So I have 4 times 3 times 2 times 1 different ways to rearrange the math books, just the math books. Oh, but this is 4 factorial. I hope you saw that before I continue. Now let's move on to the English books. So we only have 3 places for the English books, right? So we only have 3 English books. I have 3 different English books to choose for the first place, right? 1, 2, 3. So I only have 3 here. then I'm choosing from the two left, so I only have 2 English books that I could choose here. And then I just have 1 left. Oh, but this is just 3 factorial. Okay. And then the chemistry books, we only have 2 places for that, so 1 and 2. Well, you can only rearrange it in 2 times 1 way, right? Because in your first experiment, you only could choose any of the 2 to be in your first place, and then once you've chosen one, you only have 1 left. So that's 2 times 1, which is, I'll write it as 2 factorial, which it is. And then your 1 lonely history book, you only have 1 place for it, which is just 1, which actually just equals 1 factorial. So I'll write it as 1 factorial, just to, again, sort of get used to this notation. Okay. Great. So we could rearrange the math books within themselves 4 factorial different ways, right? So what does this mean? I could just move the math books like this: math 1, math 3, math 2, math 4. That's like 1 outcome of the 4 factorial different outcomes, which is 24. So this is just one of the outcomes that I could rearrange the math books out of the 24 outcomes. So that's all that means. And you know, an easier example is to see that you only could move your history book in 1 way, just that history book, just 1 history book. Awesome. So now the basic principle of counting says you have to multiply all of the outcomes for your given experiment. So our first experiment is finding ways to rearrange the math books. So doing that gives you 4 factorial outcomes. For the English books, it gives you 3 factorial outcomes. For the chemistry books, it's 2 factorial, and for the history, it's 1 factorial. So we have to multiply them together. Okay, so let's do that. Let's multiply them. Oh my god, the brackets are not working out. So 4 factorial times 3 factorial times 2 factorial times 1 factorial. Are we done? If you said yes, good guess, but we're not done. Because we only factored in if we had the math books in the first 4 slots, the English books over here, the chemistry books here, and the history book here, right? Because here, look, you're rearranging the 4 math books within themselves, sure, and you're rearranging the English books in the second slot, right, within themselves, and then you're rearranging the 2 chemistry books here, and then one history book is there. However, we didn't account for the fact that I can move these 3 chemistry books behind the math books, right? That's legal because in this example, the English books have to stay together. Yeah, but I can still move them all together behind the math books. So we have to account for all of those different switches. Like I can move all these 4 math books after the history book, and I can move the history book over here, so we could switch the places. Now, how do we do that? Well, this is how we do it. Since the English books have to stay together and the math books have to stay together, why don't we just use these letters to represent each of those English books, each of those math books, each of those chemistry books? So the 4 math books can be represented as M, as one object, because they have to stay together anyway, right? The English books have to stay together, so they're glued together. So that's just one big English letter, English object, English book. Same with the chemistry, and same with the history, and you get mech, or mech, whatever that is. But now you have 4 different objects. Oh, you have 4 different objects. So again, why are we doing this? Because we have to account for moving the books that deal with the same subject together before or after the other subjects. So I can move my math book, all my 4 math books after the 3 English books, or I can move my chemistry books, the 2 chemistry books that I have, over here, or I can move the chemistry books here and the history books, I'm not going to draw any more arrows to make it less confusing, but you guys get the point, hopefully. So, since I have 4 different objects, I could rearrange them, with slots, right? Like we did before with the permutations, with the letters X, Y, Z. If you remember that, there were 3 objects. We could rearrange them in 3 times 2 times 1 different ways. We have 4 objects now, and we could rearrange them 4 times 3 times 2 times 1 different ways. Why? In your first slot, think of your first slot as this giant slot here. Well, I could choose any of the 4 objects here to be in my first slot, right? Any of the 4. So I have 4 different outcomes. Then in your second slot, I have 3 different outcomes left. In your third slot, I have 2 different outcomes left, right? 2 different objects, C and H, and then H. Or, it doesn't really matter what you choose first. If you chose H here, you only have 3 different objects to choose from in your second slot. And then this, and then that. Oh, but this is just for factorial. Okay. So, this tells you that you can rearrange the books that deal with the same subject within themselves this many times. And you're multiplying them because these are all different experiments and you want to know how many different ways, how many different arrangements are possible here. And this shows you how many different arrangements are possible if we move all the books that are dealing with the same subject together after or before the other subjects. So, because these are 1, 2, 3, 4 experiments, and this is your 5th experiment, the basic principle of counting says you have to multiply them together. You have to multiply this by that. So let's do it. So what you end up getting is the 4 factorial from here times, so I'll put big parentheses, this beast, which is 4 factorial times 3 factorial times 2 factorial times 1 factorial. Okay? So, this was experiment number 1, rearranging the math books within themselves. This is experiment 2, which is rearranging the English books within themselves. And this is experiment 3, which was rearranging the chemistry books within themselves. And this was experiment 4, where you just have the 1 history book. And then this is experiment 5, where you're rearranging these 4 objects, but remember the hidden meaning behind each object is that they represent each of their corresponding subjects. So this big M represents this entire grouping of the 4 math books. And that's it. That's your answer. I don't know if I wrote down the actual number. No, I did not, but it's okay. If you have a calculator, you can do this yourself, or you could, multiply all this together, then multiply them, and then multiply by 4 factorial, and you get some answer. But this is the answer. That's how many different arrangements are possible. And that's it. So, I mean, it is a little tricky, but it's not too bad. Okay, so let's move on. Okay. So I just want to make sure. Okay, so this is another segue to something that can happen. So consider this. So what happens when certain objects are indistinguishable from each other? From each other. How many different arrangements does the word apple have? So think of apple like this, where it has 5 objects. The objects are A, P, P, L, and E. Well, if we went in this blindly and we just follow what we know, we have 5 slots, right? 1, 2, 3, 4, 5. Because apple has 5 objects. Once I choose a letter in my first place, right, I have 5 different choices for that, right? That's my first experiment. I choose one out of the 5 letters I have. Once I've chosen a letter, I have 4 different letters to choose from, or 4 different objects to choose from. So that's 4 times 3 times 2 times 1. Oh, but this is just 5 factorial. And we would be done. That's it, because that's what we have been doing this whole time. But there's a problem specifically with this word. Or don't think of it as a word, think of them as separate objects, right? So you have A, P, P, L, E. The problem here is that 2 of the objects, particularly P, well, they're the same letter, they're the same object, right? So, if I had one arrangement like this, apple, and then another arrangement like this, apple, and I told you I switched this P with this P, so it gave me 2 different arrangements. Well, they look exactly the same. They are the same arrangement, so we have to account for that. We have to account for the fact that these 2 objects are indistinguishable from each other. They, I cannot tell them apart. They are the same object. So we're overcounting here. This is an overcount because the P's are the same. So we have to sort of divide out the bad outcomes. How do we do that? Well, you have to figure out how many different ways do we rearrange the P's. How many different ways can we rearrange the P's in general? Well, we have 2 P's, right? 1, 2. There are 2 objects, so 2 slots. Well, I could rearrange them 2 times 1 ways, right? Because you have 2 choices for your first slot. Once you've chosen 1 P, you have 1 left, and that's it. So that's 2 times 1, which is 2 factorial. This is how much we overcounted by. So we have to divide this out. So in total, we actually have 5 factorial divided by 2 factorial different arrangements. And that's it. So it's not just 5 factorial. It's 5 divided by this overcounting. We overcounted it because the P's are indistinguishable from each other, and we have to account for it. And we just have one more definition for this, and then an example following that, and then we're done. We're done with permutations after that. So let me just erase this, and we'll do our example. First let me write out the actual, in general form. So in general, we have so the n factorial on top, right? That's how much we would actually have. And then if we have a certain number of objects that are alike with each other, so let's say the p's were alike, right? So we had the 2 factorial. But let's say other objects were alike as well. So you multiply by the other objects that were alike. Let's say there are e's that are alike. Also that would be n2 factorial. And then you have nr factorial depending on how many objects you have alike. So for example, in the word pepper, one, two, three, four, five, 6 objects. So you would have 6 factorial on top. You could try it out on yourself to see that it is 6 factorial. But the p's you could rearrange 3 factorial ways times, because they're all the same object, times the 2 e's that are alike, times the 2 factorial ways you could rearrange the e's. I want you to verify that this is correct on your own. If you don't understand why this is correct, please leave down a comment. Okay, so let's move on to our example. Okay. So here it is. A checkers tournament. Let me erase that. Okay. Checkers tournament has 10 competitors. Of which 4 Russian. So you have 4 Russian. 3 from the United States. 2 from Australia. So 2 Australian. And 1 from Spain. So 1 from Spain. If the tournament result lists just the nationalities of the players in order in which they played, how many outcomes are possible? So only nationalities are listed in the ranking. How many different outcomes are possible? How many different permutations are possible? How many different outcomes are possible? Okay. So let's work through this like we did in the last example. Let's say we just wanted to find out the total number of outcomes, right? So we have 10 competitors. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You could choose 10 in the first, 9 in the second, 8, 7, 6, 5, 4, 3, 2, 1, right? 10 to choose from in the first place, 9 to choose from in the second, 8 to choose from the third, and blah, blah, blah. Oh, this is just 10 factorial. And we would be done. However, the tournament only lists the nationalities in the ranking. Meaning I cannot distinguish between one Russian and his Russian friend. Or I cannot distinguish between the 2 Australian guys because only their nationalities are listed in the ranking. So we're over counting again. So we have to account for these indistinguishable nationalities, right? Because one Russian guy and the other Russian guy only have their nationalities displayed, and I cannot distinguish between 2 nationalities that are the same, right? Russian and Russian is the same, so Australian and Australian is the same. So we have to divide out the ones that are the same. So with the Russians, how many different ways can we rearrange the Russians? There are 4 Russians. Well, in the first slide, you could choose 4. In the second slide, you could choose 3, 2, then 1. That's just 4 factorial. And then from the USA, you should have 3 factorial because you have 3 different people from the USA. From Australia, should have 2 factorial. And then the one guy from Spain, well, you could only rearrange him 1 factorial ways. So what does this say? We have to take the actual number of outcomes we would have had, but divide it by the overcounting and multiply them together. So what we should have is 10 factorial over 4 factorial times 3 factorial times 2 factorial times 1 factorial. And the denominator comes from the basic principle of counting, because these are all your different experiments and you have to multiply them together, but we are overcounting this. We can't have this because they're indistinguishable. The nationalities are indistinguishable. So we have to divide it out from the actual number of outcomes, and you get 12,600 different rankings. And that's it. We're done. We're done with permutations. And next time, we'll be moving on to combinations. And it's not harder, it's not easier, but it's just a little different. It's still gonna take some elements from permutations and definitely from counting. So make sure you look through your notes, look at the examples we did here. Again, if you guys don't understand some of the examples, some of the explanations I have said, please leave down a comment and we'll try to figure it out together. I hope you enjoyed the video. If you did, it'll be great if you subscribe and like. The more help I can get, the more videos I can put out. And that's it. I'll see you guys next time. Bye.